Combinations. Some of you may remember from elementary school, whenever you were asked, like if you were given, I just recall drawing like a picture of like 5 shirts and like 3 pairs of pants. And how many different outfits can you make with the 5 shirts and the 3 pants? You remember that?
No. I don't know if you did that.
Y'all don't remember doing that? Okay, so we use combinations and permutations. We're going to focus on combinations today. So when we talk about combinations, we're talking about how many different ways we can do something. For example, if you go to Sonic advertises all the time about all these flavors they have, right? Mm-hmm. And they say there's so many different ways you can make a drink. Well, what they're doing, they take your total number of options, I'm going to call that N, your number of options, and then they let you pick so many. I'm going to call that R. How many you choose.
Miss McGee, can I call them to ask how many they have?
No. So what we do, we set this up, let's say that they have 25 flavors, and they tell you that you can pick any 3 flavors you want. How many different ways can you choose 3 flavors? In other words, how many possible combinations are there? Cherry, grape, watermelon. Cherry, lime, watermelon. Cherry, why can't I think of anything else? The point is, how many can you do? So what we use is this nice little formula. If you take your calculator out, we're going to use our calculator to do this rather than doing it by hand.
Wait, like our graphic calculator?
Yeah. Either or, it doesn't matter.
I didn't see your calculator, babe. No, I didn't. It's cool. I lost mine.
Dang.
I took this to the side.
So, guys, if we were to use the formula, do y'all remember what this little exclamation mark means?
Negative.
That means factorial. If I have 5 factorial, that means 5 times 4 times 3 times 2 times 1. It's multiplying all the previous numbers before.
Wait, does it start at 5 every time? Or
No, it just, you can do factorial of any number. If I did 20 factorial, that would be 20 times 19 times 18 times 17
But is it
times
doing
16
the
times
factorial of the n? Or is it going to
Yes, that on this one, yes.
Oh, you're right.
But what we're gonna use our calculator to do this. So if I have 25 flavors and I want to know how many different ways can I choose 3 flavors, then I'm gonna do 25 choose 3. Okay, and this we're gonna do it on the calculator rather than that big formula. So if you take your calculator out, your quackalator. Oh, goodness. Right, here we go. If you hit the button that says math, okay, and you go over, if you've got just a little scientific, I'll help you with it.
Ooh, I'll open it.
If you go into probability,
Wait, you need the door open?
to the far right,
Wait.
the 3rd option there.
Hey, Matt, remember your calculator?
Here's the thing though, you got to enter in first, then click on now. Before you select that,
I don't have probability.
yeah, PRB. Before you select that on your calculator, you have to do the N first.
Oh.
Okay, so you have to type the number that you're using for N. So how many flavor choices did we say?
25.
25. So I'm going to do 25, then I'm going to hit math, and then I'm going to go over to PRB and choose NCR.
Oh my god, you're speaking gibberish.
And then 3. That's amazing to me.
How calculator you just do that?
25, math, PRB, and then NCR.
That's clutch. In middle
But
school,
I'm saying, is that not crazy that they are? If you've got 25 choices, there are 2,300 different ways that you could choose 3 choices, isn't it? Yeah.
I do that on here.
Wait, what do you think?
Wait, no, I got a second. I'll show you.
Let me pause this so we're not.
Alright, so
Type your number.
So combinations, if I'm just choosing a certain number out of a pool, then it's fine 3, but at Sonic, you're not limited to 3 flavors, right? No. You could get 1 flavor, or you could get 2 flavors, or you could get 3 flavors, and so on and so forth. So we have to take that into account. This is only assuming you can only choose 3 flavors, and that you have to choose 3 flavors. Yes, Matthew.
So you're doing a 4-letter pin, like
Yes.
1 through 9 pin, or 1 through 0 pin.
Yes.
You do 4 CRN, NCR, and then 9, or 10.
Actually, 9 choose. Each spot is its own. If you're talking about a 4-number pin, I'm assuming you're talking about like an ATM pin number.
Yeah.
1, 2, 3, 4. There are actually 10 possible numbers because 0 counts, right? This would be a 10 choose 1. But what I was getting at is you have to account for these, okay? So what we have to set up is we have to set up a scenario. I always run through my head and I think, is this an and scenario or an or scenario, okay?
This is an and.
So do you 10 choose 1 and you choose another, or you choose another? Which one is it? And, because you're going to choose both of them, right? Anytime you replace and, this indicates that you multiply or indicates that you add. So what I'm going to do, I'm going to say, and this is actually a really good scenario we came up with here. Surprise, surprise. 10 choose 1, so I want to pick a number here, and I'm going to pick another number. So I've got the same 10 to choose from because I can choose the same number twice, right? And 10 choose 1, and
That's a beefy
10
number
choose
right
1.
there.
Right?
What is it?
So I'm going to multiply each time. So what I'll do is I'll do 10 choose 1, which is 10, right? There's only one combination each time if I'm only choosing 1. But what I have to do is I have to say, well, then this is 10 times 10 times 10 times 10, right? Which means there are 10,000 possible combinations of 4 numbers.
So that's smoothie.
Oh, you did
What?
choose 1 because it was 10 pounds.
Right, because 0, 1, 2, 3, 4, up through 9, right. What? Okay, but let's go back to the Sonic example. Let's say of those 25 flavors that you can choose up to 3 flavors. Okay?
This is an emergency. They even have dental floss.
Because you really have to say it in your head in order to figure out what you got to do. If I'm choosing up to 3, that means I could choose 1 flavor. Is it and 2 flavors or 2? Or 2 flavors. So or, yep, 2 flavors. Or I could put all 3 in there, right?
So 2,300 plus 300 plus 25.
Whoa! What?
I'm right.
Did you already put it in your calculator that quick?
I didn't know the 2.
Okay.
I just figured 1 is 25. I already knew.
That's right, because 25 choose 1 is 25.
25 choose 2 is 300.
The or means plus. 2 flavors would be 25 choose 2, which is what'd you say?
300.
300. And yes, we already did the 3 flavors, which was what?
1 and 2,300.
So we get 26, 25. So now we've gone up even more. So now really think about Sonic. How many, I don't know how many flavors they have, but
Well,
there's
look at
no,
Oh, it's like 300,000 something.
Yes.
so now you can test what they say when they say there's so many choices. Well, are there really that many choices? Well, it depends on how many flavors initially that you have. 52 cards. There's 52 cards in a deck. How many different suits are there? 4. So if there's 4 suits and they're evenly divided, then how many hearts do you have?
13. No, it's not 13.
Yeah.
Yeah, it is 13.
And then clubs,
13.
spades. What am I missing? Diamonds.
Diamonds.
Okay. You need to write this down because your homework relies heavily on the fact that you understand how many are in each suit. There's also on page 378, there's a breakdown of everything. How many face cards do you have of each? 3 face cards. So there's king, queen, jack. There's 4 kings, 4 queens, 4 jacks, right? 4 aces. Yes. So let's set up a scenario. Let's see if you can figure it out with combinations. Let's say you're playing with a standard deck of 52 playing cards with 4 suits and 13 different cards in each suit. How many different 5-card hands can you get? How many different ways can you get 5 cards out of that deck? This is an easy one. There's nothing else with it. What do you do?
52. Oh my God.
52.
2, 5, 9, 8, 6, 9.
Choose. What is it?
2,
5, 2,
9,
2, 5, 9.
8, 6, 9, 0.
Oh, I got
9,
9,
6.
Wait, what?
It's 9, 6.
It was
I
960,
caught a
we
little
switched it
bit
to 690.
It's
funny.
Okay, let me change this up then. How many different ways can you get a 5-card hand if with all the same color?
26.
I don't know how to do that.
With all the same color?
26 C5.
All the same color.
So it'd be
You're correct.
Oh, it's 26, 5, 7.
Right. Because there's 26 of each color. But here's what you got to think about actually. I didn't say how many different ways can you get 5 red cards. I said of just one color. So I could get 5 red or 5 black, right? Do you agree with that? Right, so then you would add the 2. So I could, out of 26, I want to choose 5, or I could do the 26 black and choose 5. Does that make sense to you? Because there's 2 different colors. Now, if I said how many different ways could you choose 5 red cards, then it would be 26 choose 5. Okay?
Where is
So
that?
you do 26 choose 5 plus 26.
Yes.
Where is that C at?
Under 30,560, which
Do we just
Yes.
do the same thing we've been using the little map?
Yes. How many different ways could you choose a 5-card hand that has at least 1 king? So you're exactly right, and that means that what I have, and this one gets really difficult, so stay with me. At least 1 king. Let's set up the different scenarios. I could have 1 king or 2 kings or 3 kings or 4 kings. Do you agree?
Or 5
Did you
years.
have 0 keys?
Or 16.
It says at least 1.
Or
Okay?
7 kings.
So I want to set up the scenario for at least 1.
Or
But
9
here's the thing. If I have 1 king, I've got to make up the rest of my hand, right?
What about
So 1 king really means 1 king and 4 others. Do you agree? Or means plus. I could have 2 kings and 3 others. I'm going to put an O there. Plus, you have one very similar to this with something about queens, I think, in your homework. That's why I wanted to do this one. Or 3 kings and 2 others, because I got to have 5 cards in my hand, right? Do you see the difference in using the and versus the or? Okay. It does, but right now we're just talking about. We're just talking about.
Well, why do we have to have 5?
Because I just said, how many different ways can you make a 5-card hand?
Oh, okay.
All right. So for now, look. Let's set this up. 1 king. How many kings are in the deck? Somebody said it. 4. Choose 1. And means multiply. How many cards are there that are not kings?
Everything before is like 48.
48. 48, choose 4. Plus, now I'm going to set the next scenario up. Okay, so if there are 4 kings in the deck, oh, Ben, don't do that. Excuse me. If there's one, if you need 1 king, there's 4 kings in the deck, so it's 4, choose 1. And I need 4 other cards. So if you don't count the kings, there's 48 left. All right, shh, guys. Come on, stay with me. All right, 2 kings would be, there's still 4 kings in the deck. This is a whole separate hand. Choose 2, and means multiply 3 other cards. So out of the 48 that are left, I want to choose 3. And I'm going to continue with this pattern. 3 kings,
How
what?
did both 48?
These are different scenarios. So this is, I'm back to the whole deck of cards. Because I can have this scenario or this scenario.
Yeah, but if that one's 48, choose 4.
No.
Shouldn't that one be like 49, choose 3?
No, because I'm assuming that if this scenario happens, none of the others happen. All right, so let's say times, now 2 others, 48, choose 2. Plus, and then 4, choose 4. Times 48, choose 1. Ben,
I'm about to develop.
come on.
Where you at?
48, choose 4 for me.
I'm 48. 4. 19, 45, 80.
Ooh. Do 4, choose 2. Y'all split this up. Ben, do 4, choose 2. Olivia, do you have it on
I
yours?
already did it 6.
All right, let's go down the road. Peyton, if you'll do 48, choose 3.
I'm about to
Grace,
say,
if
I'm
you'll
about to
do
fuck
4,
one.
choose 3. Drew, if you'll do 48, choose 2. Robert, if you'll do 4, choose 4. And Chance, if you'll do 48, choose 1. All right, 4, choose 2. What'd you get, Ben?
6.
6. What's 48, choose 3?
Wow.
Oh, 48, choose 3 is 4.
Wow. That's Peyton's.
No, 48,
Oh,
choose.
I'm sorry, hold on. All right.
You did 4, choose 3, I think.
I have 48.
48, choose 3,
I have
and
4, choose 4.
17,296. And the
What?
next one's 4.
And the next one's 4. What about 48, choose 2?
1128.
1128. How about 4, choose 4? How about 48, choose 1? 48. All
I
right.
had it, but then I didn't extra.
Ben, instead of putting Tetris on that calculator, multiply these numbers together for me. You should still have 194580 on your calculator. Times that by 4 for me. Just hit times 4. No, don't clear it. Just hit times. Oh. Okay.
Ooh.
What do you get?
77,832. I don't want to have to like say the whole number.
Now multiply the other one while I answer Touchdown's question. And is multiply or is add?
What do you want me to do?
6 times 17296.
Can you 3776?
How about 4 times 11, 28?
4, 5, 1, 2.
Now add all these together. 7, 7, 8,
7, 7, 8.
3, 2, 0. Plus.
Plus 10 something.
Yep, 10, 3, 7, 7, 6.
Plus 4, 5, 1, 2. Equals.
Plus 48.
88, 66, 56.
Woo!
Zooey mama.
If I need to get at least one king to win whatever card game I'm playing, there are 886,656 different ways of getting one king.
That's so cool.
Out of how many? How many did we say? How many different 5-card hands are there in a deck altogether?
Less than that.
2,598,000. But you bring up a good point, Drew, because what are the chances now? How do you figure out the chance? It's probability. So what is this divided by this? What's 886,656 divided by 2,598,960? What do you get?
Divided by
34%.
You have a 34% chance whenever you are randomly handed 5 cards of getting at least one king.
We're not gonna have Friday.
Pretty cool, right? I think that's pretty cool. I think it's pretty cool to figure out things like that.
That's kind of hard.
It is a little difficult. Triangle.
Sounds hard. I bet this is gonna be like triangle. You made it more triangle. You made it more.
I just changed my mind. I couldn't. It will hurt my heart to leave it out.
It hurt my heart when I looked at it.
Here's what we're gonna do. We're gonna form this triangle, and this is so neat the way it works out. All right. You have to remember that we have Pascal's triangle. We always start with ones.
lesson we're learning this year?
All right.
Matthew, slow down.
Here's how we form Pascal's triangle. We start with a 1, and on the first row, we're going to make it up with ones. All right. You have to remember that the outside numbers are always ones. Okay. Here's what we're going to do. Come out one more, write a 1. You're going to add the 2 above it. So 1 and 1 is 2, and add a 1 on the outside. Okay. The pattern's going to stay like that every time. Add a 1 on the outside. 1 plus 2 is 2 plus 1 is add a 1 on the outside. We're kind of going between the numbers that are there. 1 on the outside. Now 1 plus 3 is 4. 3 plus 3 is 3 plus 1 is
4.
Okay, let's go another row.
How many rows do you have?
1.
I think like 8, maybe 8 or 9.
24.
1 and 4 is
4.
4 and 6 is 6 and 4 is 4 and 1 is 1 on the
So
outside.
this can just go forever.
Yes. I want to take you up through a few here because I want to show you what we're going to use it for. 1 and 5 is
6.
5 and 10 is 10 and 10 is 10 and 15 is 10 and 5 is 15. 5 and 1 is 6 and 1. Let's do another row. 1 and 6 is 7. 6 and 15. 15 and 20. Are you starting to see a little bit of the pattern emerge here? No, but it's symmetric and yeah, exactly. 28, 56, 70, and then it just repeats here. 56, 28, 8, 1. This is, well, technically it's 8. We start everything at 0 in Pascal's triangle. Okay, and you have to remember that. Now, I want you to do something for me. This is so cool. This is so cool. I want you to name the position by rows and columns, if we start at 0 every time, of this number right here. What row is that? Start at 0. 7. What column over would it be? How many over is it if you start at 0 again? We'll put C for 0, 1, 2, 3, 4, 5. Take out your calculator.
Oh, it makes you. Let's see.
And do 7, choose 5 on your calculator.
21.
Haha, 21.
Isn't that amazing? It works for every single one.
Wait, what?
It's because you said 21, man.
The row with the column over that it is. This is just a list of combinations. This is 0, choose 0. This is 1, choose 0, 1, choose 1. This is 2, choose 0, 2, choose 1, 2, choose 2. This is 3, choose 0. You got it?
That is very.
So tell me, without using your calculator, what do you think 8, choose 5 would be? By the way, this row of numbers indicates the row for you, or that diagonal. So 8, choose 5, 0, 1, 2, 3, 4. Yep. This is 8, choose 5. Verify on your calculator.
Wait, listen.
Yeah. 1 is always 0, yep. Isn't that cool? I think so too.
That is very cool.
I'm not gonna want to write that out on the test. Not gonna lie. I'll just plug it into the calculator.
Let's say that I had x plus 4 raised to the 5th power. Tell me, if you had that, what that means you have to do.
X plus 4 times X plus 4.
X 5 times, right? Each time that polynomial is getting longer and longer, but I can only do 2 at a time. Well, here's where Pascal's triangle comes in and helps us. Here's another helpful use of Pascal's triangle. If you go to this row of Pascal's triangle, 5th row, the 5th row is 1, 5, 10, 10, 5, 1. We're going to use that to expand this binomial, and it's a binomial, so we call this the binomial theorem. Okay. All right, so here's what we do. These are coefficients that we're going to use.
Miss, we have a quick question.
How do you turn them, Ben?
What? Okay,
How
no, stop, no. First coefficient is 1. I take the first piece of the binomial, which is x. Okay? I'm going to raise it to the exponent that's already there that I started with. Okay? Then I'm going to take the second piece and I'm going to raise it to 0.
What's up, Sam?
Okay? I start with the exponent that I started with, the row from my Pascal's triangle. Okay? Now, what's going to happen is I'm going to go to I've used this coefficient. Now I'm going to use the 5. Matthew, you were going to ask me about this on your quiz, and I am not going to tell you. 5. Take the x. This always stays. Start counting down on the x. So it started at 5. Now this is going to be 4. The 4 is going to count up, so it's going to be 1. I'm subtracting from this one. I'm adding to this one. Okay? And by the time I get to the end, they will have switched flip-flops, switch places. So now the next one is 10. X, it's not 4. Now it's going to go down another, but the 4 is going to go up 1.
You're just writing numbers and frequencies right now. I don't know what's happening.
Okay.
You're going so fast.
I understand what's happening, and I wasn't even paying attention.
This 5, yes, this 5 goes out on the first one, and then I start at 0 for the second piece. Okay? The exponent on the x is counting down. The exponent on the 4 is counting up.
Oh, then you're going to go 10, 10, 5.
Yep, and I'm using these coefficients. Shh, Ben.
So how do you get the exponent?
You start with the one you started with here, the 5, and 0. The second one's always 0. Then the first one counts down, the second one counts up.
Okay, got it.
All right. So I've used 1, 5, and 10. 1, 5, and 10. Now when I go to 10, the x is going to count which way, up or down? So what does it become? 2. What's going to go on the 4? Next one's 5. What's going to go on the x? What's going to go on the 4? The last one's 1. What goes on the x? What goes on the 4? They have officially swapped places. Okay? But I have to simplify now. And I know this seems like a lot, but at the end of the day, it is still way easier than multiplying this out 5 times. I promise it is. Oh my goodness, it gets long. All right, so exponents come first. 4 to the 0 is 1. 1 times 1 is 1. So the first term is x to the 5th. Now I have 5 times 4 is what? 20? X to the 4th. Plus 4 to the 2nd power is 16. And 16 times 10 is 160. X to the 3rd.
Wait, I thought you were multiplying the coefficient and the exponent.
Well, 4 to the 2nd power is 16, and then I multiply it to the coefficient.
Oh, I see.
4 to the 3rd is 64. Times 10 is, hello, 640. What's 4 to the 4th? 256. What's 256 times 5? 2,560? No. And then what's 4 to the 5th?
Yeah, you can't lie. He's always trying to.
What's 4 to the 5th? What is it? 1024. There it is.
Bam!
Does it get harder than this one? Yes. This one was hard because it was a 5th power. There could be coefficients in front of some of these. This could be 2x. Okay. There could be a minus sign in the middle. Let me do one with a minus so you see, and I'll be done. I know this was a loaded lesson for a Friday. It is a lot, yeah, but nothing on its own is too hard. It's just, there's a lot of patterns with this.
Can you go back to just the
Yeah.
Jacob,
All right. This time the exponent is 3. Tell me the coefficients that I'm going to use.
1, 3, 3, and 1.
1, 3, 3, and 1. When you have a minus, you must change it to a negative for the second term, or else this isn't going to work. All right. Change it. Do a same change kind of thing, so that your second one is negative. All right. First coefficient, 1. First term,
2x.
What's the exponent that goes on the 2x?
3.
3. Next term, negative 3. What's the exponent that goes here? 0.
Wait a second. How about that?
Now the pattern continues. These two things stay the same. The coefficient changes and the exponent change. What, Ben?
Why did 3 go over the 2x about 3?
Because you always start with this exponent on the first term.
3.
But does it not go wrong?
No, only to the first term. 2x, 2, negative 3, 1.
Yeah, I know how to do it with the
3,
So,
What goes here? 2x. 1. Negative 3. 1. What goes here? 2x. 0. Negative 3. 3.
Wow. So they just, the exponents just switch spots.
Yes. Now, because I'm multiplying, guys, please stay with me. Because I'm multiplying inside this parenthesis, this exponent can distribute. So this becomes 2 to the third, which is what?
It's 9.
8. X to the third and negative 3 to the 0 is 1. Plus. Now here's where it starts getting tricky and you have to be very careful. And I'm going to do this in 2 steps. This becomes 3 times 4x squared times negative 3. Yes.
Times 4 equals 11.
3. 2x to the first, negative 3 squared is positive 9.
But do we not combine like on the other one, the negative 3 and the
We're fixing to. I'm doing it in 2 steps so you can see. Then stop. 2x to the 0 is 1, but negative 3 to the third becomes negative 27. Okay? Now let's clean it up. 8x cubed. 3 times 4 is 12, times negative 3 is negative 36x squared.
11.
Plus 3 times 2 is 6, and 6 times 9 is 54x minus 27.
It's like